Okay, so I will continue from the last part of the lecture, and we have shown that the heat conduction equation is proportional to surface cross-sectional area. It is proportional to temperature difference, and the inversely proportional to the thickness of the material. And now I will add one more concept about this wall material here, and that last concept will be that K. Okay. This is the new concept and the important concept in fluid mechanics, the heat transfer, and this case called thermal conductivity. So it is the thermal conductivity of the material. So you will see that it is the property. Okay, this is the property of the material, and this property it can be a function of the temperature. It can be a function of the pressure. Okay. And then this relation here that we've shown as the Q.C.D is equal to thermal conductivity in the cross-sectional area, delta T by del X, is called the Fourier's law of heat conduction. Fourier's law of heat conduction. Okay. And this Fourier's law of heat conduction, this is the, simplified form. But in reality, the Fourier's law of heat conduction is something like this one. Q.C.D is K AC and the dt by dx. So I've written here AC, but it is not the AC, but it is the area that is, let me just erase it. This one is the area normal to heat flow. So this one is area normal, or you can say perpendicular to heat flow. So in original form, it is something like this one with a differential equation where it shows the change of temperature with respect to x. Okay. Now we will talk about the thermal conductivity of the materials, and we will see how the thermal conductivity of materials depend on the temperature and how it happens. And there are similar concepts to thermal conductivity, and this is electrical conductivity, how the materials conduct electricity. Okay, and there is hydraulic conductivity, how the materials conduct the water. So I can just give you, this one is about electrical, it is very easy one. And for hydraulic conductivity, I say that I have a glass, something like this one, and inside this glass here I have these are all, just finish it. These are all soil. Okay, and this soil, or it can be any different material, and at this here you have that water here that enters to that soil. Here you have the water inlet, and you will have the water outlet here. Okay. And this, due to this water inlet and outlet, here you have this delta P of water. This soil conducts water through it. This conductivity depends on the properties of the soil or any other material. Therefore, the similar concept of electrical conductivity can be hydraulic conductivity, which is used in hydrology. I've written this one twice, it is wrong. And the similarity with this one we can prove is that heat conductivity. How the material is able to conduct heat, to let the heat flow through it. Okay, this is called the heat conductivity. For the heat conductivity, I've given just some values for it. So for the air, this conduction coefficient is small. You can see it is 0.026, and its unit is watt by meters Kelvin. And you can determine its unit from this equation here, that Q dot has a unit of watt, and the area has a unit of meter squared. dt by dx, it will be the delta T, you can think this one as delta T, with a temperature of Kelvin, with a unit of Kelvin, or it can be degrees Celsius, it doesn't matter, divided by the meter. Okay? And you will have that unit of the conductivity. And from here, you can determine that the conductivity has a unit of watt meters by Kelvin. Or it can be watt-meters by degree Celsius. For air, it is very, very low. If the conductivity of the material is very low, we call it as insulator. So you can, this one is as insulator. Okay. It is almost insulated. It doesn't let the heat flow. Water is 0.59. It is approximately 0.6. You can see the ratio between air and the water. So that conductivity of water, you can divide by conductivity of air. It is 0.5948, and this one is 0.02623 times. You see that it is very large number. The conductivity of water, so this ability to conduct heat. This one is ability to conduct water fluid. This one is ability to conduct electricity. And you can see water is 23 times more than the air. And the brick that we are using in our house, so that has a conductivity of 0.72. Glass fiber, it is an insulator material, and this has a 0.038. Okay, the glass fiber is insulation material. And the copper, you can see it is a very high number. Aluminium, 200, it is high. Gold is 80. And the wood, the oak tree, it has 0.18. And the iron is 80, and nickel is 91. And here you can see that the copper has a conductivity of 397. Let me just show it. This one has a 397. The conductivity of nickel is 91. Okay, but when you mix it, so this one will give you an alloy. And for the alloy of copper nickel, you can see that 70% of copper and 30% of nickel. When you mix it, you will get the conductivity, which is 29.75. You can see it is smaller than both of it. For nickel, 91. For copper, 300, 400. At the end, you get lower than both of the values of the alloys here. So that therefore, the conductivity of the alloys, so it is not expected to be more than the smaller conductive material. Okay, so it is not a say that linear behavior. So you cannot expect that if I mix this one, I will get more conductive material. Or the bronze. Okay, this is also an alloy which has a 79.92. Okay, the bronze has a different material inside it, but for example, it has the copper here. So it is more than the conductivity of the is less than the conductivity of the copper. Okay, much smaller than this. Is that the copper doesn't affect, for example, nickel. It doesn't affect the bronze conductivity again. Okay. So that aluminium 200. Separately, the materials have the higher conductivity than the alloy itself. Now the conductivity K of the liquids. So we look at the three separate cases, that the K of the liquids and the K of the gases and the last one K of the solids. So in this case, we are looking at the atomic view. Atomic view. In this atomic view, in the macroscopic view, it is clear. It is ability to conduct the heat. But then what happens in an atomic level? For the kinetic theory, so this one approximates the conductivity of the gases, K, as the F divided by the 3 diameter squared, and the Kb, the Boltzmann constant, to the power of 3, and temperature, and the pi to the power of 3, and the mass. So you can see that here the conductivity of the gases is proportional to temperature, but inversely proportional to mass. So the lighter materials have higher conductivity. This one is the first result from this one. Lighter gases, they will have the high conductivity. Okay. This is the first result from the kinetic theory of the gases. The second result from the kinetic theory of the gas is that if the temperature is increased, then what will happen is that the conductivity will increase too. If you increase the temperature, the conductivity increases. But it is opposite behavior with the mass or the molar mass. If you increase the molecular masses, then the conductivity will drop. Liquids follow the similar tendency to gases, but it is complicated. Okay, and there is no explicit pattern. You cannot say that the liquids follow the same pattern as the gases, but they are very similar to this one, but they are very, sometimes they're, for example, for water. You cannot say the clear pattern for water with respect to other liquids here. For the liquids, it is complicated, but for the gases, it is simple, and it is given us with this relationship according to the kinetic theory of the gases. Okay. So last one is there for the solids. So, but we should note that for the gases and the liquids, the conductivity, heat conduction happens through molecular collisions. Here you will have the molecular collisions, the colliding of the molecular with another one. So during this collision, you will have the transfer of kinetic energy. Since the higher temperature means, I should add this one here, that the higher T means higher kinetic energy. Okay, and the higher kinetic energy means that this molecule here can transfer its energy to the next molecule here. Okay, and it is the molecular collision, and the diffusion is also in its way here, because that in the molecular level you will have the diffusion of the heat from one molecule to the another one, but this one is a very, very slow process. This one is very slow process, and it is random. Okay, it is random process, very slow process, and it is, you know, that we call it this one as the stochastic models. Okay, these are stochastic models. And for the solids, it is very easy one. So it is happening due to free electrons. We have the free electrons inside the solid material. These free electrons are moving in the lattice pattern here of the solids, and as they move, they carry energy with itself. So you can call this one as energy carriers. So they are carrying energy with itself from one place to another place, and therefore they are carrying the heat. And also the lattice vibration, the configuration of the solids, the lattice itself is vibrating. As it vibrates, it carries, it sends off waves. Okay. By these waves, you are carrying energy. Again, this one is the energy carrier. Okay, so these are the conductivity of the solids, liquids, and the gases. And on the other side, so we can divide the materials as the insulator. We can the good conductors, okay, and we can say that the superconductors. Okay, insulator means that, for example, the gases. So I can give one example, air. You can see that air has a conductivity of 0.026. So 0.026 watts by meters Kelvin. You can see it is a very, very small value. Therefore, air is like an insulator. It doesn't allow heat to flow. The good conductors can be the metals. The metals are the good conductors of the heat. Or for iron, it is 81. For nickel, 91. For aluminium, 235. And 396. And the superconductors is that the K value is very, very high. Okay. There are also the superconductor materials, but you get these superconductor materials at the laboratory conditions. Okay. And it can be at the higher temperatures, it can be at different conditions, that you reach a point that the material is becoming very, very conductive. Okay. So you can see that you have two extremes. In one part of the extreme, you have the insulator, and another part of the extreme, you have the superconductors. Okay, and here in good conductors, there are two famous materials, which is the aluminium versus the copper. Okay. If you compare the conductivity of the aluminium, it is 235, and for the copper, it is 397. But you should remember that this conductivity, as I said here, so the conductivity is function of the temperature and the pressure. Okay, Conductivity is function of temperature and the pressure. Therefore, if you change the pressure, the conductivity may change. If you change the temperature, but it depends. Okay, for example, for gases, so for gases, I mean the gases here, the ideal one. For ideal gases, the conductivity is only function of temperature. Okay. But for metals, it is function of temperature and the pressure. So if you change the temperature, conductivity changes. The materials that I've listed here, all of them, the conductivity value is shown as 25 degrees Celsius. Okay. These are the values at 25 degrees Celsius. And the aluminium has 235 watts by Kelvin, meter Kelvin at 25 degrees Celsius, and the copper at, but this one is at 25 degrees Celsius. But when you look at this one, you will see that the copper has higher conductivity than the aluminium. But in the engineering, what you are interested in is that, firstly, you are interested in efficiency. This is the engineering principle. And the second one is that the cost. Okay. And sometimes what you are doing is that if the cost is high, you are, that you leave the efficiency out. For example, in this case, copper is more conductive than the aluminium, but it is expensive. Okay. Therefore, since it is expensive, in most of the structure, we are using the aluminium. Okay. But this one is cheap. Okay, now we are looking at the one extreme of the conductivity of the materials, where you have the insulators. There are different types of the insulators. You can see that we have the glass wool, but in all of these insulators that I've given here, the main principle here is that we have the trapped air. Okay, you are trapping air at some place because the air, you can see, it has a very low conductivity. So it is very, very low. If you trap air, and then you will have it will drop the conductivity. So for example, if you look at this, the glass wool here, this one is the glass wool. Okay. In this glass wool, you have the glass fibers. These are the glass fibers. And in that glass fibers, you have here you have air pockets. Okay. These air pockets do not allow the heat transfer. They stop it. The glass fiber itself has the low conductivity, but the main thing here is that the air pockets. These air pockets stop the heat transfer, and therefore it acts as an insulator. Or the wool here, so that the wool or the fur of the animals. You can see again here you have many trapped air. So this one is the air pocket. So these air pockets inside these fibers, so instead of glass fiber, now you have the fur here, okay, hair. Let's say that. Now you have the hair, and so at each hair you have the trapped air, and this trapped air decreases the amount of the heat transfer from the body or in opposite direction. Okay. And similar to this one, the double pane window, you have one pane here, you have another pane here, and in between here you will have this air. Okay. So when you have the heat transfer from this double pane window, you have the heat transfer in that direction, you have the heat transfer in that direction. When you have the heat transfer, this air, due to low conductivity of the air, since air is insulator, okay, so the Q drops. So if you remember the equation, Q dot is the K and the cross-sectional area delta T by del X. Okay. This K is low, and since it is low, if these are very high, it doesn't matter. It will drop the coefficient here, and therefore you will have the lower amount of the heat transfer. Again, here you have the trapped air. Here, you can put different gases here. It doesn't matter that it will be air. The main principle here is the gases. So when I say that the insulator, there are the gases. You can put, for example, here the helium, or you can even put a vacuum here. Okay, but as I said, efficiency and the cost. So if the cost is too high, then you have to leave out the efficiency concept, and you have to go to the cheaper ones, which is the air that is available everywhere. Or the styrofoam cups, the glass. As you can see, this one is the styrofoam, this one. And again, in this styrofoam, if you have, that cracked this styrofoam with your hands, you can see that it is like that. You can feel the air pockets here. You can see it. Again, you have the air pocket here. Okay. And these air pocket stop the, the heat transfer, and it acts like an insulator. And I will give you just one more example and finish this concept here. Say that you have the sunlight here. So this is the sun, and let's say that this is the earth here, and here you have the vacuum. Okay, and here you have the around the earth you have the atmosphere with a layer of the here air. Okay, and as I said, if there is no wind, okay, if there is no any wind, then the energy from sun that you feel is only the radiation. Okay, so that it is not only, let's say that it is mostly radiation. Why it is the mostly radiation? Because that, as I said, the air, this one has a low conductivity, low K, very low K actually. And since it's very low K, in reality, what is the heat transfer? Heat transfer is conduction and plus radiation. Okay. You feel the heat from the sun due to conduction and the radiation. But since the conduction part is very, very small, this one is very small, and the radiation part is the important or the dominant part. Therefore, the energy that you feel from the sun, that energy that comes to you, is only by radiation. The conduction part is very small. Or you can say that the bonfire. Okay, if you are very close to the bonfire or the hot stuff, if you put your hands on the hot stuff, the conduction part is very small. You only feel the radiation part, because the air, wherever you have the air, the conduction is small. Therefore, the energy that you feel comes mostly from the radiation. All of these cases, what I mean is that if there is no any wind, okay, or motion, it should be stationary. If there is motion, then it will be a different concept. Okay, so another fluid concept is the thermal diffusivity. And for the thermal diffusivity, here we are talking about how the materials diffuse heat. And so let me first give its definition. So here you have the conduction. You compare the conduction versus that is storage. Conduction capability, okay, versus storage capability. Okay, and this one is defined by the K. And how do you store the energy? Store energy by Cp, specific heat value, to make the, and this one will have the mass, the density here. Density is inertia. Inertia plays a significant role in storing the energy. So that therefore the K by rho Cp is the thermal diffusivity of the material, and it compares how the material conducts heat versus how the material stores heat, and it is shown with the letter alpha. You can compare the alpha of the materials here. You can see that the glass fiber, that is very, very small. For all of the materials, the copper, it is a bit higher. That is the alpha is actually a small number. Actually, it's a very small number. But at the end, you can see the ability of the material in conduction versus it is storing ability. Okay. So I can give you just one example where the thermal diffusivity may be important. Is that example that? So that is, so when you cook food. Okay, when you cook food, what will happen is that you have the pan here. This is the pan. And inside that pan, you have the water. And you are transferring heat. So that, let's say that this is the heat that you are transferring to that pan here. Okay. So if the alpha is very, very small, what it means is that the material here, say that this one is the material that you are using. Let's see the two cases. When first case is that very low alpha. And the second is that very high alpha. Okay, and when the alpha is very low, what it means, the material stores energy and it doesn't conduct it to the water side. It stores the energy inside it. It doesn't conduct energy. Therefore, it is not desired. Okay. What you want is that this material here should conduct heat to the water side, and you should boil the water as well as cook the food. Therefore, the very high alpha is the desired one. So let me just do one example for you and then talk about the convection, which is another concept in the thermal energy heat transfer. The example is that I have a wall here. This is the wall. And for this wall, and has a thickness of, that is 40 centimeters. On one side of the wall, I have the 40 degrees Celsius. This is the wall, okay, cross section. And in some way, I have determined that inside the wall, the temperature drops linearly. And it drops linearly to a value of, let's say, 5 degrees Celsius. Okay. And the question is, so if I give you the height of the wall is that, height is that 3 meters, and the width of the wall is that, let's say, 5 meters. Okay. So the question is, what is the Q dot CD through the wall? Okay. Let's analyze this question and find the answer to it. So for the wall, so let me just write firstly energy equation. So that Q dot CD, it is that K and the area that the heat flows, and dt by dx. Always we start with the general case. Okay, dt by dx is the general one. Delta T by delta x is a special one. Okay, and since the temperature changes linearly here, you can see that it changes linearly, and it drops from 4 to 5. Okay, negative. So then this one will be equal to the conductivity of the material that we don't know, and the cross-sectional area of the material is that, the wall is that, with a 3 meter high and 5 meter into the page, it will be 15 meters squared. Okay. And the dt by dx, it will be that 5 minus 40. Okay, and the delta t by delta x is that 40 centimeters minus 0 times 10 to the negative 2. Okay, so that this is 15 meters squared, and the dimension also, you should be very careful about the dimension. It is 40 centimeters. It should convert into meters. Now the K value here. And for the wall, a wall is not a plain structure. It is a complex. So that structure here, you don't have the, so here will have the brick, you will have the gypsum, and you will can have the foam, for example, etc. Okay, but in our case, we will say that it is simple. We will simplify it, and we will say that it is brick. But there is only brick, and if there is only brick, we can put the coefficient of the brick here, which is that 0.72. But you have to remember that, so this 0.72 is at 25 degrees Celsius. Okay, if you want more accurate value, to get the more accurate value, what you will is that the K will be at T average. Okay, what's the T average? T average is that 5 plus that 40 and divide by the 2, and it will be that 22.5 degrees Celsius. Okay, we can get it from table. But for this type of materials, you don't have this, that this resolution. Okay, you have, for example, from 20 you go to 40, from 40 you go to 60. Temperature changes more in the tables. But anyway, by using linear interpolation or by any other methods, you can find the K value in a more accurate manner. So if you calculate the QCD by the conduction through the brick, and if you tell me the value of it, 945 watts. Okay, good. This is the QCD heat loss. This one is the heat loss from room. Okay, heat loss from the room by 1 volt. It is 945 watts. What you can do is that, for example, so you are trying to look for the air conditioner. Okay. So you will have that 3 volts. Okay. For that 3 volts, you can calculate that QCD. Okay, and then from that QCD from volts, and also window, you have to calculate it. For window, it will be also again the Q.CD plus Q.CV. Here you will have that other type of the heat transfer, and then from the adding these heat transfer values, you can get air conditioner power. You can calculate it. This is the step that we are doing for calculation of the air conditioner cooling capacity or heating capacity. But one thing here you should notice that you can neglect the floor, because we are assuming that from the floor the heat loss is very small. But so you can do more, that detailed analysis, and don't neglect the floor, and add also the roof part, and get the amount of the heat transfer from the room. And from that amount of the heat transfer, heat loss, you can determine the capacity of the heating of the heat pump required for the location. Okay. So the next part is the convection. Convection is the energy transfer, second type of the heat transfer mechanism here. And this one is actually not type of the heat transfer. Okay, it is not, that pure heat transfer. Okay. The general definition is that it is energy carried piggyback, okay, on the fluid moving across the boundaries. It's like an energy piggyback on the fluid. It is not the that pure heat transfer. Okay. You will see how it happens. So conduction heat transfer, this one, it happens due to diffusion. Okay. Diffusion means that, if you remember, it is at molecular level. Okay, if I go back to here, the conduction, for example, for liquids, you can see the molecular diffusion and the molecular collisions. All of them are diffusion stuff. And the solids, lattice vibration, free electrons, and all of them are the diffusion stuff. Okay, this is the conduction. And then we say the convection. Okay, and the convection is that 2 parts. Here you will have the advection. I will say what advection is. And here you will have the diffusion. Okay, diffusion part is the conduction part. Okay, and the advection part is that the fluid motion. It is the motion of the fluid. Let me just give you one example and then talk about this convection concept. And to say that, example is that, so you have injected, that the ink. You have injected ink on water. Okay, let's think of 2 cases. The case A. Okay, water is stationary. Water doesn't move. Okay, now if the water doesn't move, the ink will spread by diffusion. It will be by diffusion alone. Okay, there will not be another concept here. In the second case, and the water moves, water flows. If the water flows, what will happen is that the ink will be by, so you will have the advection concept. Advection concept is that the water motion, due to its motion, it carries the ink from one place to another place, and also it helps the diffusion of the heat, the spreading of the ink. So it will help the spreading of the ink, and due to advection, advection is that the water flows, and plus diffusion. At the same time, you have the molecular interactions, molecular diffusion, and as well as the advection, the transfer of the heat. You see that piggyback, the same stuff, piggyback. It is the piggyback on the water. So this piggyback is the ink here. That ink is taken from one place to another place, but during that motion you have also diffusion. The same happens, the two concepts happen at the same time. Okay. Let me just give you one more example here about the convection and the conduction stuff here. I will talk about this double pane window. So this is a double pane window. You have the one pane here, which is glass. You have another pane here, which is another glass here. Let me just show it here. Double pane window. Okay, in double pane window, there is a, just erase this one. So I have a glass here. This is the glass. And you have one more glass here. This is zoom in. I have zoomed in. Glass 2. And in between, you will have the air. Okay. And if the air here is, so let's say that the glass 1, this one is at 5 degrees Celsius, and the glass 2 is at 0 degrees Celsius. Okay. And if the air is here stationary, that is stationary air, then you will have the heat transfer from that system. That heat will come it Q dot, will come that place and leave it. Okay. This Q dot, it will be only by conduction. This will be only by conduction. Okay. This is the first case. Now let's see this second case. I have the same window, but it is, the distance is more now. Okay. I have the glass 1 again. I have glass 2 again. And the temperature here is that same temperature, 25 degrees Celsius. I have the 0 degrees Celsius here. And I have the, inside that one, I have again the air. Just add it. But here the air is not stationary, it moves like a loop. The air rises here due to temperature, it has low density, it rises, and it takes a loop here, and when it touches, the density drops, and it drops down, and then it's dragged due to moving air here. So you have the loop of air. Air, you know that is. So here you have the air rotation. Now you can see that inside the system, the air motion happens. So the air moves. So therefore, here the heat transfer, Q dot, out of the system, Q dot, it is due to convection. Now it is convection. So convection means that here you will have the diffusion or the conduction and plus the advection. Same, that is same event and the same process, but here air is stationary, therefore it is the conduction only by conduction. But here it is the convection process, and the convection, I mean that it is diffusion, and when you say diffusion, it is conduction plus the advection. In all of these cases, you have the conduction, but here it is pure conduction. So that pure conduction, but here it is not pure conduction, it is that pure conduction plus the advection process. Okay, now the equation for the convection heat transfer, it is very, it is called the Newton's law of cooling. Okay, and this equation is determined as that the Q dot is equal to the surface area and multiplied with Ts minus T infinity, and where Ts is surface temperature. Okay, and here you have the one more coefficient here, which is the H. Okay, and this H is convection coefficient. Okay. H is convection coefficient, and it is not the property of the fluid, and it is determined by experimental. You can see the differences. It is not the property, property of the fluid. But when I go back to the conduction coefficient, it is the property of the fluid. So the thermal conductivity, it is property of the fluid here, and then therefore it is heat transfer process in conduction. And also this H value here, this H is a function of fluid velocity. Okay, it is the function of the fluid velocity. I mean, if you increase the fluid velocity V, if you increase it, and then you will also increase the convection coefficient, because they are proportional. The proportional, I mean, it is not the linearly proportional, it is a non-linear relationship. Okay, these are determined experimentally. You have to notice it. It is experimental property because it is very complicated. And the complication comes from that here you have the fluid motion coupled with heat flow. Okay, so therefore it is more complex than the conduction heat transfer process. So I will do one example for this convection process and finish today's lecture. Just 1 minute that I will add the slide here. Okay, so that, as I said, for the convection, so this one is complex, okay? And the complexity comes from the fluid flow and the heat flow. Okay, they are coupled. They happen at the same time. At the same time, you have heat flow. At the same time, you have the fluid flow. Therefore, the convection process is coupled, and this H coefficient, therefore, it is determined experimentally. Let me just give you one example. And the example is that outside part of the wall. Okay, outside part of the wall, let me just show you that here. So this is the same wall here. You have the 5 degrees Celsius. This is at the surface of the wall. Now 40, I will draw just the same picture here, same photo here. But you have to know that. So I have the 40 degrees Celsius here. I have 5 degrees Celsius. The dimension is the same, 40 centimeters. And the height is 3 meters, H is 3 meters, and the W is, this one is height. And the width is, that is 5 meters. Okay. And outside part of the wall, outside part means that, you can see the 5 degrees part. And there is a wind blowing. Here you have the wind that blows over it. So this one is the wind. Okay, as I said, if you increase the velocity, the heat transfer coefficient increases, H increases. Okay, and therefore the wind blowing over this one, let's say that it has a velocity of much 10 meters per second. Okay, and in some way you know that. So there are tables for this one, and you determine that H value is given as, let's say that 20 watts by meter square Kelvin. And you can determine the unit again from the equation here. So if I just write the equation, Q dot is equal to H and the surface area and the Ts minus T infinity. Okay, and the Q dot is watt and the H is, let's say, unknown. This one is that meter squared, and the distance difference has the Kelvin. You divide it, you will get the unit of the H. And H is given as 20 watts per meter squared Kelvin. But you have to know that this 5 degrees Celsius is at the surface here. But the environment may be at lower temperature. For example, here you will have the 0 degrees Celsius. Okay, this is called the T infinity. It's 0 degrees Celsius, and it is far away from the wall. So that is, wall effects are not felt. It is far away from the wall, that is the infinity temperature. It is also called the ambient temperature, or the temperature of surroundings. Okay. Surroundings temperature is 5 degrees, 0 degrees Celsius. But the temperature at the surface of the wall, this 5 degrees Celsius is at surface of the wall. Okay. Then I can find this Q dot, and that Q dot will be equal to the H value, which is given as 20, multiplied with the surface area, the same surface area. It will be that 3 into 5 will be 15, multiplied with the temperature difference. Temperature difference now will be Ts, which is 5 degrees Celsius, and T infinity, which is 0 degrees Celsius. Okay, and therefore it will be that. and 300 and 1500. This is the heat transfer that happens at the outside part of the valve. And it is only due to convection. I should add the CV sign here. It means that it is only due to convection. Okay. And for the convection part, we have the two types of the convection. And the first type is the free or the natural convection. And the second type of the convection is that forced convection. Okay, free or natural convection is that it. So just let me give you a forced convection example. For forced convection, you are using some means, mechanical means. So, for example, fan. So you are using the fan. By using fan, you are use mechanical means to increase velocity of fluid. You are increasing the velocity of the fluid by using some fan. If you increase the velocity of the fluid, and you also increase the H value. Okay, that is the forced convection. And you have also the free or natural convection. It is happening. So let me just give you an example for this free or natural convection. Again, the glass example here. I have the coffee here. And this one is that hot. And this, say that the surface is somewhere around here. And at the surface, you have here you have the 60 degrees Celsius. Here you have the, let's say, 20 degrees Celsius. And since the temperature here, it is 60 degrees Celsius here. The 60 degrees Celsius, it is 20 degrees Celsius. And the 60 degrees Celsius, air is lighter. Okay, lighter means that density is low. Okay, since the temperature is high and density is low, therefore air rises. Okay, and this air here, it rises. Okay, as it rises, the upper parts of the surroundings, and you will have this convection. Okay, this is the convection, and the famous example is the wind. Okay, wind is free convection. It arises due to temperature difference, and that temperature difference is creating the density difference. The density difference, due to that density difference, air rises. And you can see this one in the, you can see that steam over T. If you see that steam over T, it means that steam carries energy. Okay, this steam is not the heat. It carries energy. I've said it, you have to remember it, piggyback. Okay? Steam is not the energy. The steam itself carries the heat energy. Okay? Steam is not the heat. So with this one, I finished the convection part, and next lecture I will talk about the thermal radiation and the introduction to thermal radiation, and then we will move on to more deeper concepts of the fluid mechanics. Heat transfer. If you have questions, you can ask.